Hello my friends, I welcome you all to the video lectures of chemical kinetics. So these video lectures are the part of our first year undergraduate chemistry curriculum. So today is our first lecture and we will start with the discussion of preliminaries. So preliminaries mean that this is the basics of chemical kinetics that most of us might have learned during our high school, or we may not have learned. So it doesn't matter. So we will try to brush up our memories. So we will focus on some very basic information from lecture 1 to lecture 3, and from lecture 4 onwards we will build up with more and more advanced materials. Okay, so let's start with the preliminaries. So first of all, what does the word chemical kinetics mean, or what does the phrase? So the word chemical kinetics actually denote it is the subject that studies the speed of a chemical reaction. Okay, so this is very simple. Now the question is that why do we need to study the chemical kinetics? So why? And at this time point, probably there is one major answer that we can think about, that this subject helps us to determine or to find the mechanism of a reaction. Okay, the mechanism of a reaction, of a chemical reaction. So how it does that? During this course we will take a glimpse of it. So we will learn a little bit about it to determine the mechanism of a reaction from chemical kinetics. Okay, so the next question is how to represent a chemical reaction in terms of its speed. Okay, so therefore we can assume that there is a chemical reaction. There is a reactant A, it is changing into reactant B, a very simple chemical reaction. So how we can express the rate or the speed or the velocity of this chemical reaction? So remember, all these three terms, either rate or speed or velocity, represent the same thing, that is the rate of the reaction. So that means it is denoting some change. So change of what? It denotes the rate of change of the concentration of A that changes. So that means since with time the concentration of A would decrease, so we have a negative sign here. So minus it is the change of the concentration of A over time is equal to, it is the rate of formation of the product B, or the change of the concentration of the product B with time. Okay, so if we are to express this change or rate in terms of a graph plot, how would the plot look like? So for example, this is my time axis. So here time is 0. So at time t is equal to 0, we may assume that, and this is my concentration axis. So there is some point, the initial concentration of A, and we call it A naught. So at time t is equal to 0, we have A naught, and B is equal to 0 because the reaction has not started and B has not been produced. So as the time advances, we will see the concentration of A naught, or the A, would decrease and the concentration of B would increase. So the question is, how does it fall with time? Okay, so in majority of the cases we will see that it actually follows a curve. It's like an exponential fall, and the concentration of B would start to rise kind of like this way. This is in an exponential manner. So this curve represent A and this curve represent the concentration of B. Okay, all right, so this is how the reactant or the product would change with time, and this is how we can represent them graphically. But there is one exception though, in which the fall of the change of A or B with time would not look like this. That means it would not look like it would not follow this kind of curvy way. Okay, so in course of time during our lectures we would find out where does that exception occur. Okay, so after this we would now try to look at that is there a generalized way to represent a rate equation. Okay, so let's now take a look at that. So here we see how in a generalized manner a rate equation can be expressed. So before we begin, so let's once again remember our graph plot where we have represented the change of the concentration of A right here from A naught with respect to time, provided the reaction was something like this, A going into B. And we saw, and actually we stated that except in a certain case, in all other cases we will see that the concentration of A would be falling down like this. So it's kind of an exponential manner. So that means the change of the concentration of A is dependent on the power of something, power of some concentration. So from where we can logically guess that there is a general way to write a rate equation. So once again, we assume a reaction A, converting it into B, and let the concentration of A at any time t is represented by C. Okay, so here the rate, or again the speed of the reaction, we can write this is minus dA dt, or we can still write minus dC dt because we are expressing it in the change of the concentration of A, so that's why the negative sign. And the generalized way of writing this is minus dC dt is equal to a constant K C to the power of n. Now this to the power of n actually coming from the generalized observation where the curve follows a kind of exponential decay. So the thing is, what are K and N? So now let's define that K is a constant and it is known as the rate constant, and C is the concentration, and N is called the order of the reaction. Okay, so therefore the generalized rate equation, so we can take that as the generalized rate equation. Now depending on the order N, we can call the reaction by its specific name, so we can categorize the reaction. For example, N can be 0, so we can call it a zeroth order reaction. So we can write it's a zeroth order reaction. N can be 1 and we can call it a first order reaction, and it can be 2, we can call it a second order reaction, and even N can be fraction. Okay, so it would be called as a fractional order reaction. Okay, and then this K is the rate constant. So the question is, how constant is the reaction? So let me tell you, K is actually a function of the temperature T, and also it is a function of the, obviously the reactants, means the specific reaction that we are talking about, and of course it is also functional on the catalyst if any catalysts are being used. So for a particular set of reaction, that is A goes to B, here it is already decided whether there is any catalyst or no, and the reactants and products, that means the mechanism is also fixed. So that means for such a fixed kind of reaction, the rate constant is only the function of temperature. Okay, so unless and otherwise mentioned, the rate constant is only the function of temperature. So the next question is that, for example, if my chemical reaction is represented by like this, for example, A plus B plus C, and it is making a product P. Okay, so the three reactants making a product P, and then if someone expresses the rate is equal to the change of the formation of the product, that is dp dt, okay, is equal to K concentration of A to the power alpha, concentration of B to the power beta, and concentration of C to the power gamma. Okay, so the same way, this is also a kind of generalized rate equation for three reactants making a product. So the question is, can we determine the order, means from this generalized rate equation where alpha, beta, gamma are known, so can we predict the order? Okay, yes, in that case the order will be the summation of alpha, beta and gamma, so the summation of all individual powers, so whatever it is, it would give you the overall order of the reaction. For example, if it is the C term is not there, it is CACB, and this is 0 and this is 2, so the total order would be 2. This is 1 and this is 1, the total order would be 2. Okay, so now we have an idea what the order of it is, then how it is represented. It is represented by the letter N. Now the question is there any way that we can guess or determine the order of the reaction from the stoichiometric formula of the given reaction itself or by any other way? So let's check it out. So the question was that from the stoichiometry of a given reaction, can anyone predict the order? So here, if we look at the examples of these three reactions, you see for the first reaction, 2 HI molecule is giving H2 and I2. So here it says the N is equal to 2, that means the order is 2. Okay, so it matches. But here you see, by looking at this reaction, an order is 1, so no way we can predict the order from the stoichiometry. And also at the last reaction, you see it also doesn't match with the given stoichiometry order, but even here it is the fractional, that is N is equal to 3 by 2. So the answer is that no, order can't be predicted from a balanced equation. So that means from the stoichiometry, that is number 1. All right, so what is the definition of the order then? Okay, so the order, it is defined as it is the concentration terms or the number of the concentration terms on which the entire reaction depends. Okay, and the order N, it is applied to all of the reaction overall. So we do not talk about, even if these reactions are multi-step reactions, we do not talk about orders of a particular step, rather than the order is applied to the all of the reaction. Okay, so the question is once again that even if we know the mechanism or the mechanistic steps of the reaction, then is it possible to predict the order? And the answer is yes, sometimes it is possible, but in order to get that, we have to introduce a new term which is called the molecularity. Okay, so here we are now going to discuss a new topic, that is molecularity. So for that I need to clean the board and I have to begin from this end. Okay, so we are now going to define the new term molecularity. So before we begin defining it, so let's remember our previous example that we have already mentioned about. It is the dissociation of hydrogen iodide, and we already know that it's a second order reaction, N is equal to 2. So hydrogen iodide dissociates into hydrogen and iodine. So let's take a look the exact mechanism of the reaction, how it happens. So we can now imagine these two HI molecules, okay, kind of as an illustration. These two molecules, they have to collide for making a reaction. So they collide in a single step and then they form the product. Okay, So the product is like this: hydrogen gas and iodine molecule. So what happens at the point of collision? So at the point of collision, we can think that there happens a hypothetical structure. We can call it a transition state, where at some point all the atoms are thought to be interconnected. So these two HI molecules in a single step collide each other to form this. Okay, so the entire transition is a single step process. Okay, so now what we see, in a single step there are two molecules, 1 and 2, two molecules reacting to form a product, and we also saw that the order is equal to 2. So from this, that we can try to make a correlation between the order and the molecularity. We will come to the definition of molecularity now, but before that we can tell that in a single step reaction, okay, the order is equal to the molecularity of the reaction. So what is the definition of molecularity? So the definition of the molecularity is, it is the number of molecules or atoms or ions that collide with each other in a single step to form the product or for proceeding the reaction. Okay, so remember that these number of molecules, atoms or ions would define the molecularity, provided it collides in a single step. Okay, so molecularity is a concept where it is applied on a particular or a single step, and molecularity is a number. It can be a fraction, it's always a whole number, because it is the molecule, and it is not applied to the overall reaction. It is only applied to a single particular step. Okay, so what we learned, that in a single step the number of molecules colliding with each other straight away gives you the order. Okay, but you can ask me that this is a single step reaction, so what happened with the other reaction? Okay, so where we did not get the order n is equal, did not get the order matching with the stoichiometry of the reaction. So let's recollect that particular chemical reaction once again, and it would help our understanding on molecularity even better. So that reaction was the dissociation of nitrogen pentoxide N2O5. It dissociated into nitrogen dioxide and oxygen gas. Okay, so here order was equal to 1. So obviously we can tell from our knowledge of molecularity and order that this is not a single step reaction. Definitely, because had it been a single step reaction, then n should have been is equal to 2, but it is not the case. So that means this is a multi-step reaction. So let's try to guess the steps, or let's try to write the individual steps of this particular reaction. So what happens that when N2O5 starts to dissociate, it first, in the first step, it gets dissociated into NO2 plus NO3. Okay, and then this NO2 and NO3 further collide with each other to form, once again, it forms NO2 plus oxygen and plus NO once again. Okay, so now what happens in the third step? This NO and this N2O5 further reacts to give you 3NO2. Okay, so if you add up these individual steps, so this is step 1, step 2 and step 3. So if you add up these individual steps 1, 2 and 3, you will end up with this particular stoichiometry. So now here you see the molecularity M for the first step is 1, and here molecularity for the first step is 2, and here also the molecularity of the third step is also 3. But here we saw the N is equal to 1. So then can we relate, or how can we relate that this order should be the molecularity of, or why should we only consider this reaction where the molecularity matched with the order? Because further mechanistic studies reveal that out of these 3 reaction steps, this particular step, that means the first step, is the slowest step. Okay, so what happens in such kind of multi-step reaction, that the molecularity of the slowest step becomes the order of the overall reaction. Okay, so we now learned a new interesting fact, that is, for a multi-step reaction, the slowest step of the reaction and the molecularity of the slowest step becomes actually the order of the reaction. So therefore, having learned few facts about molecularity and the order, so we should be able to differentiate between order versus molecularity. So there are some clear distinction between these two. Okay, so as I have told you from the beginning, that order is an experimentally determined quantity. This is a purely theoretical concept. Order is applied for the overall reaction. This is applied for the particular steps, and order can be 0, 1, 2 fraction, but molecularity cannot be 0 and it cannot be fraction. It is always a whole number. So the difference between order and molecularity sometimes are favorite questions of the people who sets questions for exam papers. Anyway, but before that, before we proceed, so once again there is one more question to you, that I have also mentioned such reactions, okay, as an example of the order. And remember, the order of this is 3 by 2, that is 1.5, and this is a fractional order. So definitely you may question me that being it single step or multi-step, the order comes from the molecularity, right? And molecularity is always a whole number. So even if we think that this reaction is a multi-step, then how come molecularity being whole number, the order becomes a fraction? Okay, so that means it apparently contradicts the statements that we have just learned. Okay, so the answer is that this is an exception. Why exception? Because this particular type of reaction falls within a category. The special category is called a free radical chain reaction. So for a free radical chain reaction, we are unable to frame or unable to determine the order from the mechanistic step or the molecularity of the slowest step. We don't go into that direction. We calculate the order directly from the reaction data. Okay, so it is n is equal to 3 by 2 is determined from an experimental perspective, and why the n becomes 3 by 2 we will learn that later during this course. Okay, so for that, for the time being, we learn that molecularity is equal to the order of the or order is the molecularity of the slowest step does not hold good for a free radical chain reaction. Okay, so the next topic is how can we predict or rather how can we write the rate expression from a stoichiometric equation. Okay, so in other words, we have a stoichiometric general equation, so we can write that as alpha A plus beta B is giving me gamma C plus delta D. Okay, so how we can express the rate of this chemical reaction incorporating the stoichiometric coefficients. Okay, so that is how we actually express it: minus 1 over alpha dA dt is equal to the rate or speed is equal to this is equal to minus 1 over beta dB dt is equal to 1 over gamma dC dt, and by writing the square bracket I am denoting the concentration of D or concentration of the species is equal to this. So this is always true for any stoichiometric reaction. We have to use this kind of generalized rate expression. Okay, so this is equal to we can write that the rate constant multiplied by concentration of C to the power gamma multiplied concentration of D to the power delta. Okay, sorry, since we are using this minus term already, so here we can also write that this is equal to, so this, or we can write K Ca to the power alpha and Cb to the power beta. Okay, so this is the same thing. Okay, so anyway, if this is true, then can we, for our own little exercise, if we look at this reaction. Okay, so this is the dissociation of bromine molecule into two free radicals. Bromine 2 is dissociating into 2Br dot. So can we find the rate of formation of bromine, that is what is dBr dot dt, means the bromine free radical, or in other words, if we go to the reverse one, that is if 2 bromine dot 2 Br dot giving you Br2, so can we find the rate equation of dBr2 dt? Okay, so I want you to find out the correct rate expression using K concentration of Br dot or Br2 with respect to time. Okay, so you have to take the help of this little formula. Okay, so please find it out, and we'll later check your answer that whether this is correct. Okay, so now we would move into the method of expressing integrated rate law. So far whatever we have been discussing, the rate equation or rate expression, so this is called rate expression, these are nothing but a kind of differential equation. So for particular cases like for zeroth order, first order, second order, we have to solve this differential equation. Solving means you have to integrate to find a integrated rate equation. So the purpose of the integrated rate equation is to find what is the concentration of the product or reactant after a certain time t. Okay, so let's work it out. So right now we will derive the integrated rate law for each of the zero, first and second order reaction. So we start with the zeroth order reaction. So as I told you earlier, the goal of the integrated rate law is to have a standard expression or basic formula in which we can predict that how much of the reactant or the product is there at the reaction after a certain time t, and vice versa. So here A is going to be, and the condition is at time t is equal to 0, we express A is equal to the initial concentration A naught, and at time t is equal to t, the concentration of A is denoted as AT. So the differential equation first that we are going to write is very simple. Rate is equal to minus dA dt, that is the rate of disappearance of the reactant, is equal to rate constant multiplied by A, this concentration of A, to the power of 0. We are writing 0 because we are already dealing with the zeroth order reaction, so we put n is equal to known value 0. So therefore in order to solve it, that means we have to integrate that. So or minus dA over A naught. So we can actually so dA over A, yeah, so dA over A is equal to K dt. So now we have to integrate, and while we do the integration we have to put the limits of the integration. So the limits for t was 0 to t, and for this thing we have A naught to A over A t over here. Okay, so if we integrate that, okay, so finally our value should come here as A naught is equal to, or rather AT is equal to A naught minus KT. Okay, so the equation that we got here, okay, we can call it, it is the integrated rate law of the zeroth order reaction. Okay, so once we get it, then therefore there are a few more questions that easily coming up. So the question is, can we plot, or rather can you plot to show that what would be the graph plot of AT versus time t? Okay, and not only that, what would be the plot of the rate of change of the equation, I mean the rate of change of the reaction, sorry, dA dt versus t. So that means we have to plot two things, that is the concentration of A at any time t versus time, or the rate of the equation, or the rate of the equation itself versus the time t. Okay, so once we draw the graph plot, we would be able to see that with change of time something doesn't change, so that remains constant, and something becomes something decreases with a straight line. Okay, so from that probably you will be able to guess that at the very beginning when we draw the when I drew the manner that how the concentration A falls with time t, whether this is true in this case. Okay, so you can easily draw the graph plots and you can find it out. So with that thing, there are a few more questions, that what is the unit or the dimension of the rate constant K. So can you determine it? So from this equation you can easily determine the unit of the rate constant K. So it's for your own exercise, so I'm not going to write down the answers here, so you will try to find it out later. So one more thing I would like to draw your attention here, that for an integrated rate law there is one more aspect that we deal with. This is called the half-life. So the half-life is defined as the time it takes the initial concentration A naught to become exactly A naught by 2. So can you find the time t at which the A naught becomes A naught by 2? Okay, so you try to find the expression for the half-life from this. So for zero order reaction, the issue of half-life is not that important, but for the first order reaction definitely the half-life denotes a very one of the very important parameters. Okay, so this is how we get to the integrated rate law of the zeroth order. So now from this reaction, so as you can see, this would give you a graph plot of a straight line if you plot AT versus T. So from here, if you know the rate constant and A naught, you are adding the concentration, so you know it, you can easily predict AT at any time t, and vice versa. You can predict how much time it would take for AT to get to the certain percentage values. Okay, so next we define or try to derive the integrated rate law of the first order reaction. Okay, so I realized that there was a mistake while deriving the zeroth order reaction. Although the final expression was correct, but minus dAdt is equal to Ka to the power 0. So a to the power 0 is equal to 1. So we should not write any expression of a here, any a term. So therefore, it reduces into minus dA is equal to k dt. And then we integrate with the limits 0 to t here and a naught to at minus, okay, and then once we integrate that, we get into the final form of the integrated rate law of the zeroth order reaction. Okay, so just sorry about the mistake, so I have corrected it here. So now let's proceed to the first order kinetics. Okay, so if we try to derive the integrated rate laws of the first order reaction, so we write minus dAdt is equal to Ka to the power 1 here, so that's is equal to K to the power Ka, and or minus dA over A is equal to K dt, and then we try to integrate that with the limit 0 to t and A naught to A, and therefore this becomes minus d natural log of A. And if we integrate that, we comes to this expression, natural log of a naught over at is equal to kt. So this equation is known as the integrated rate law of the first order reaction, and it can be represented into two forms. One is the linear form, that is natural log of at is equal to minus kt plus natural log of a naught, and exponential form where at is equal to a naught e to the power minus kt. So therefore, once we get these two forms, obviously there is the question of graphical presentation. So now from here, can we represent the graphical plot of AT versus T, number one, and of course whenever we have the linear form, that means ln AT versus T. So that means this ln AT versus T would give you a straight line, and of course you have to qualitatively draw the graph plot to show how these two plots look like. Okay, so once we get the integrated rate law of the first order reaction, obviously we have to address some of the relevant questions. So these relevant questions, number one, that is what is the half-life, okay, in the first order reaction. So you have to show the half-life T half is equal to 0.693 up to this approximation divided by the rate constant K. Okay, so from the integrated rate law, by putting the condition of A naught divided by 2 at time T half, you can easily get this expression. And number two is what is the unit or dimension of the rate constant. Okay, so the unit of the rate constant, you will see that it comes as the second inverse or the time inverse. Interestingly, if we take the inverse of k, the rate constant, it gives you the time dimension. So the inverse of first order rate constant is only time. So this time, this parameter is also known as tau, and this tau is called the relaxation time. Okay, so this relaxation time is a parameter. Sometimes it is important, but it is only relevant for the first order reaction. So just for the definition, we remember the inverse of k is known as the relaxation time. Okay, so now the question is, what are the examples? Okay, so the examples of the first order reaction is this one. Okay, so we have already learned it is the dissociation of N2O5. It dissociates into nitrogen dioxide and oxygen. This is one of the example, and another example is the dissociation of H2O2. so it dissociates into H2O plus oxygen. Okay, so these are all the classical examples of the first order reaction. And I think I forgot to write the examples of the zeroth order reaction. So here we go. So the example of the zeroth order reaction is this. This is called the reverse Habers process. So you know the Habers process is which we form the ammonia. So the reaction, the Habers process reaction is like this. So from N2 and H2 we form the ammonia, and the example of the zeroth order reaction is actually, it is the inverse or the reverse of Haber's process. So it is basically the dissociation of ammonia into the nitrogen and hydrogen. Okay, so this is an so examples of zeroth order reactions are rare, but still it happens. And so one of the classical example is the uh, reverse Haber's process. So the next topic of our lecture is that uh, is there any alternate form for expression of the first order chemical kinetics? Okay, so this particular topic we are going to address in the next lecture, that is the lecture number 2. So I will upload these video lectures in the form of archives to some online portal, and I will share you the links, so it would serve as a ready reference for you. So no matter when, or no matter at what places you are currently at, from there you can access those video lectures at your own convenient time and whenever required, before exams or after exams, whatever. So I hope these video lectures would be of some help to you. So during our discussions in online platform, I will mention the required textbooks. So you please go through the lecture materials, that means the video lectures and the textbook, and keep yourself up to date in studying. So I will see you in the next lecture. Till then, goodbye.